Okay, good afternoon. I hope you are rested and ready for the last 3 hours. The first one will be an interesting one on flame instabilities. Probably will go over an hour, but we'll see how it goes. And those are two nice pictures of unstable flames. The one on the left is a diffusion flame. It's the planar unstrained flame that I spoke about yesterday, which when it's stable is just a planar disk, and then it becomes unstable under some condition, and it takes on this cellular appearance where it burns in this region, and in between it's a very weak burning, almost near extinction. And then this Bunsen flame that is typically a cone, a smooth cone, and here it becomes cellular, or well, polyhedral rather. In other words, the base becomes cellular, and it's formed of this section along the cone rather than a smooth cone. So these are complicated structures that we need to understand, first of all, why they are created. In other words, what's the condition under which the flame becomes unstable. And of course, their description involves more multidimensional structure, and so that's one of the reasons that it's interesting to study this flame. Of course, they start to become turbulent, and so that's a simplest maybe version of a more corrugated or turbulent flame, if you like. So we will start with the Dario-Landau instability, which has been discovered in the late 1938 by Dario, and in the early 1940s by Landau, by pure theoretical papers, which they have concluded that essentially planar premix flame are always unstable. Implication is perhaps that they should be always turbulent, or whatever the implication is, but planar flame has been observed in the laboratory, planar laminar flame, and so those papers have put some confusion, if you like, in the community. Why then, if the theory predicts that they're unstable, but we see them, so what's the explanation? And for at least 15 years or so, that has not been totally understood. In fact, really a complete understanding of this has only been developed in the 70s. So the Dario and Landau paper is very well cited in the literature, because under many circumstances we see the consequence of this instability. And so we'll try to describe it first in these next few transparencies. So in their description, the flame was treated as an interface separating unburned from burned gas, very much like the hydrodynamic model that we have discussed a couple of days ago. So here is the surface separating unburned burned gas, and the equation that describes the hydrodynamic flow is essentially the Euler equation on either side of the discontinuity, and the Rankine-Hugoniot relation across. In addition, they made this hypothesis of the constant flame speed, namely that every point along the flame propagate at the laminar flame speed, at the same constant laminar flame speed. And we have seen few examples of this model that indeed describe many flames, like the conical burner flame, and so on. I have given few: a spherically expanding flame, flames in counterflow, and so on. So the idea, the idea in stability theory is to perturb a basic state, or a simple smooth solution, which in this case would be a planar flame, to introduce some disturbances, because in reality there are always disturbances in every experimental setup, unless you take really very careful measurement to avoid them, but they are always there, either because of imperfection in the system, or the mixture is not exactly homogeneous, or because there is a bit of disturbance in the room where the experimental facility is taken, whatever the condition is. And so the question is if these disturbances grow in time or they decay. If they decay, then if all disturbances decay in time, then the planar flame will remain the stable solution and will be observed in reality. However, if the disturbances grow, then the planar solution will never be observed because it is always subject to disturbances that kick it away from the planar form. The simple example in dynamics is a pendulum. The mass of the pendulum is in equilibrium due to gravity on one side and the tension on the bar on the other side. There are two equilibrium states, in fact. One is the regular pendulum, where the mass is at the bottom, and the inverted pendulum, where the mass is on the top. Now, you never see a pendulum with the mass on top, and the only reason for that is that that equilibrium is unstable. Any small disturbances will kick it down. It will oscillate for a while and then settle at the lower position, okay? So the planar flame has been described within this context of a hydrodynamic model, and now we introduce some small disturbances. And in stability theory, the first question is to say, well, suppose that the disturbances are small, and let's see what is the consequence of small disturbances. But of course, once an instability is set up, the next question is, okay, well, what does the solution develop to? So that is usually the more difficult question to answer because that involves what we call non-linear stability theory. Okay, so we first start with the linear stability theory. We take the solution, the planar solution, which is denoted here with the bar. So remember the solution was that there's only an axial velocity, SL, of the incoming gas, and then the hot gas expand and move at a velocity sigma times SL. And since the gas is coming exactly at the laminar flame speed, then a planar flame is stationary and stabilized at some position that we call x equal to 0. And as a consequence, there is a drop in pressure across the flame, and we discussed that this week in more detail than that. So we introduce small disturbances, and the disturbances are denoted by prime. So it's u prime of x, y, and t. The disturbance are two-dimensional disturbances here, and they vary in time clearly. And the flame now is no longer flat, but is described by this function. So the F is the surface of the flame, which is corrugated and vary in time. And so the next thing is to introduce the disturbance in the governing equation to neglect nonlinear term, because we are assuming that the disturbance is small, so nonlinear terms are neglected, and to solve the linearized problem that result. I'm not going to go through the detail of the equations, but here is the equations were written in the previous slide. Here are the Rankine-Hugoni relation, where again we delete or cancel, neglect the nonlinear terms, and we end up with this relatively simpler problem, relatively simpler because these equations are now linear. Okay, and the jump relation across the flame identifying what happened to the disturbance. So one has to solve essentially these three boxes. Now I want just to, make you aware of a couple of things that I will need in a few minutes again. What this condition is, it states essentially that the axial perturbation in the axial direction does not vary from above and behind the flame, right? In other words, it's conserved. On the other hand, the tangential component suffer a jump. In other words, the tangential perturbation, right, above the flame and below the flame is not the same, because remember now the flame is tilted, And these conditions are expressed at the mean location x equal to 0. So when you express the tilted flame, the transverse component, if you express it at the mean position by Taylor expansion, since those disturbances are small, it gives you this jump relation. The next one I want to point out too is that the motion of the flame, which is F sub t, is exactly equal to the perturbation of the axial velocity. In other words, any disturbance in the flow just convect the flame in the same direction, okay? In the direction of u. Okay, so now when we introduce a disturbance, usually we introduce it in the form e to the iky plus omega t. Those are known as normal modes. E to the iky means that the transverse direction, in the transverse direction, the perturbation are like sinusoidal, okay, with some amplitude, with some wavelength lambda, which is 2 pi over k, so k is the wave number, okay? And we introduce periodic disturbances, and so this is the source of e to the iky, and then we assume that the growth is exponential simply because this form is acceptable as a possible solution of the linearized equation. Since the basic state is time independent, then the equation are constant coefficient. Constant coefficient admit exponential solution. Now, we use the complex form of e to the iky instead of sine and cosine simply because it's easier in the analysis. As a result of that, the growth rate, or omega, is a complex number that have a real and imaginary part, and the consequence of this, I think, will be discussed in the next transparency. So all velocities and pressure are expanded that way, and the flame position is also written in this form. So A is essentially the amplitude. Okay, just a side comment here. As I said, I used two-dimensional disturbances, but really the result is also true for three-dimensional disturbances. In other words, disturbances that vary in y, but also in the other direction, z. And the difference is simply if it's both in y and z, then you'll have here the dot product of the wave vector, which is a vector in the yz direction with component k1, k2, multiplied by, or dot product with z, which is the two transverse direction. And the only difference in the analysis is that instead of k being the wave number, k is the essentially the resultant of that vector. So it's in fact the square root of k1 squared plus k2 squared. So the result that I'm presenting are as well good for three-dimension disturbance. Now, I said that we introduced those normal modes. Being exponential solution, it's very simple. When you substitute this in the PDEs before, the d by dy immediately is replaced by ik. I'm sorry, no y. I made a mistake here in writing. So d by dy is replaced by ik and d by dt by omega. So when you substitute in the equation, you end up with ODEs. So it's relatively easy to solve. However, the problem involve also some boundary conditions and the Rankine-Hugoniot jump relation across. Now, since these conditions are also linearized, then, well, it's really this transparency that I wanted, what's on top, what I wanted to point out, is that, of course, if the perturbation is zero, if there is no perturbation, then the equation must admit that as a possible solution. So non-trivial solution is solution of this equation. And so if trivial solution is solution, what's the question? The question is, are there any non-trivial solution? And under what condition they will be? So, so the answer is that, well, the problem is therefore an eigenvalue problem. And the answer is that for some growth rate, there will be a non-trivial solution. And that relation of the growth rate as a function of the other parameter in the problem, this functional dependence is usually known as a dispersion relation. So there is a dispersion relation that tells you what will be the growth rate as a function of the wave number and the other parameter in the problem. Now, the model that we have used have only two parameters, the density ratio, which is sigma, or if you like, the heat release or the flame temperature, and the flame speed, SL. Those are the only two parameters in this hydrodynamic model. Anything else is not here. In other words, there is no diffusion or anything like this in this simplistic model. And so those are the two parameters that you see here. So the question is to find the dispersion relation or omega as a function of these parameters. I want to back up for a second and then return to the slide. Remember, I said that omega is complex in general, so we can write it as real plus imaginary part. And so, for example, the flame shape is the amplitude e to the iky plus omega t is going to have the imaginary part combined with this e to the iky and then the real part. And what we are interested is the behavior of the solution or what happened to the disturbance if we wait long enough. If we wait long enough, does the solution decay or keep on increasing? So the important thing to find out is the magnitude of the real part of omega. If the real part of omega is negative, then of course this solution will decay in time, and as t goes into infinity, it's going to go to 0, the disturbance disappears, and the basic state is recovered. The imaginary part is only an oscillatory factor, and so that's not what determines the long-time behavior. And so the important question to ask, is omega r negative for all values of k? In other words, all disturbances need to die. It's enough that one disturbance grow that the solution is unstable. So we need to find omega r negative for all k. The next slide here, I discussed the dispersion relation. So before we compute anything, in fact, we can make a very simple statement about the dispersion relation from dimensional analysis. You see, omega has units of being a growth rate, has units of 1/2, right? And so what other combination here can provide a 1/2? Sigma is dimensionless, is a ratio of densities. So you can construct a time unit from those two quantities, SL and K. In fact, SLK give you exactly a 1/2. And so from dimensional analysis, it's clear that omega will be proportional to SL and proportional to K. But we don't know the constant of proportionality, and without solving the problem, we don't know if it's positive or negative. And so clearly that's very nice, but the answer is still require solving the mathematical problem to find out the sign or the behavior of this functional dependence on sigma. So this is essentially the problem that we are facing. I'm not going to go through the algebra, and before, in fact, even showing you the answer, I want to show you some argument that will explain what is the result that we are going to see. I did mention those two jump relations on purpose before because they are important in understanding this picture. The first one say that the flame is convected with the velocity perturbation in the axial direction, namely in the up and down direction, right? The second one say that there is a difference between the tangential velocity ahead and behind the flame when you evaluate it at the mean position, namely on this dotted blue curve. And the difference is proportional to f sub y, okay? There is also a negative sign here with f sub y. Now, when you have a variation or jump across a surface in tangential velocity, essentially this sheet is a vortex sheet, because essentially what it says is there is concentrated vorticity, which we will in fact describe in a minute, which is this, along the sheet with no vorticity elsewhere. That's known as a vortex sheet. And so the question now is, here is the vortex sheet. What is the sense of the vorticity? What is the sense of this rotation? Well, the sense can be found exactly from this jump relation. In regions where the slope of f with respect to y is positive, then the difference is negative. So in this region where it's the slope is positive, then V prime at 0 plus must be smaller than V prime at 0 minus, as you see that I have drawn here. At region where the slope is negative, it's the reverse. So this is larger than this, and so on. So clearly the vorticity sense here is going to be clockwise, and here it's going to be counterclockwise. And so you see the clockwise and counterclockwise vorticity cause a perturbation in the axial velocity in this direction. And since the axial velocity is the one that convects the segment of the flame which is pointing towards the burned gas, then this segment in time will be extended further up, and so the flame will be more and more corrugated and more unstable. The reverse is true at this point because this is counterclockwise, this is clockwise, so it will be pushing the flame in this direction, and so on and so forth. And so that's essentially the origin of the instability. Now, of course, the origin is in the fact that sigma minus 1 is not 0, namely that there is a density jump across. So the origin of the instability is in thermal expansion. Thermal expansion causes velocity changes across the interface that create an effective vortex sheet at the mean position, and that vorticity is the one that distort the flame front and make it more and more unstable. And so the flame, according to this description, will be always unstable, and that's in fact the result that we are going to see. Now, there is only one thing missing in this description, in that I told you that the vortex sheet is concentrated vorticity along the sheet. But what if there is vorticity, and remember we did discuss that there is vorticity created at the flame, and so there will be vorticity in the burn gas. How does this vorticity affect the answer? Well, this simplistic argument does not give an answer for this. Really, you have to do the calculation. My point is that it's very nice sometimes to put this simple argument because they explain what you observe, but they are always missing something, or they are not always complete, because if they were, then you may not need to solve the problem, and the problem is more complex than that. In other words, there are multiple effects, they're coupled together. Luckily, what happened is that because the density of the gas in the burnt region is smaller because of expansion, then the vorticity in the burned gas expands out, and the magnitude is usually lower than what is produced at the flame, and so their effect is really it cannot counter effect the creation of the instability. There is in the literature, this is my favorite actually explanation. There is in the literature another explanation. Oops. Oh, here it is. Another explanation. And the other explanation is based on the fact that since the streamline are deflected towards the normal, then if you take a segment like this, which is pointing toward the burned gas, then the stream tube will expand. If the stream tube expand here, eventually it will have to become of the same size that it was originally. And as a consequence, there is an area increase here, and therefore a velocity decrease. And because of the velocity decrease, then this segment of the flame encounter a lower velocity, and so it will speed up because it has to propagate at the laminar flame speed according to this model. The problem with this explanation, even this explanation is not, if you like, 100% complete, because it assumes that this stream tube area change and so on. Based on this, I argue it's larger and therefore the velocity is smaller. It's assumed that this is a stream tube, doesn't change in time. But being a time-dependent problem, this argument is not complete because there are variations in time. So the deduction that I deduce about the velocity from the area is not for a steady flow. However, if the disturbance, if the growth rate is small, you can consider that as being a quasi-steady condition, and under this condition there will be an acceptable answer. But you see, there is in every explanation of this kind, there is a bit of incompleteness, so to speak. Again, the answer is that if we solve the perturbed problem, so we satisfy, we perturb here are the solutions for the pressure, velocities, and so on. It involves constant of integration that need to satisfy the Rankine-Hugoniot relation. And when you satisfy the Rankine-Hugoniot relation, you get a matrix, 3 by 3 matrix here, because I left only C1, C2, C3 as the unknown, but sometimes you can also put the amplitude as an unknown, so it will be 4 by 4. What I did, I substituted for A from one of the other relation, but it's all equivalent. Anyway, to find non-trivial solution, meaning solution where the constant of integration are non-zero, which means that you have a perturbation which is not identically zero, the determinant of this matrix must be singular, or the determinant should be equal to 0. And if the determinant equal to 0, then you obtain the expected dispersion relation. Omega hat here is just a division by KSL, so it's the dimensionless version of it. And the solution of this equation, there are two roots, plus and minus, and so there are two growth rate, if you like. One of them is always positive, and that's all that counts. The fact that there is a negative one does not mean anything, because there is one which is always positive, meaning there is a growth rate, there is an omega, a value which increases in time. And so this is that constant that was, if you like, missing from the dimensional analysis argument. So the conclusion is, which is known in the literature as the Dario-Landau instability or the hydrodynamic instability, is that all planar flame are unconditionally unstable. In other words, they are always unstable. Okay, so here are few. What you see is that the growth rate is linearly proportional to k, which means that it increases linearly with k, which means that k small is long waves, k large is small waves. So you see that the small waves, disturbances with small wavelength, in fact, grow faster than disturbances of long waves. But there's something incomplete in this, because the short wave eventually will be as small as the flame thickness, and so they will affect the detail inside the flame thickness, which is not in this description. And so clearly, the result fails when k becomes sufficiently large, and this is really part of where the resolution is. The resolution of that difficulty is that there may be stabilizing influences on the small scale, on a scale which is comparable to the flame thickness, that were not taken account in the Dario-Landau discussion. Okay, so first of all, despite what I just said, that there may be stabilizing influence that we have not covered here, the Dario-Landau instability have many ramifications in combustion, and a few of those things I will show you in the next few slides. So if you take a flame, you perturb the flame, and this flame is propagating down, so you start with some sinusoidal, and you ask, how does the flame propagate in time? Based on this Dario-Landau model, namely based on this hydrodynamic model, where the propagation, the flame propagate at the laminar flame speed, the constant laminar flame speed. Means every point on this surface, right, will propagate with the same vector down. Now you see that those parts which are more convex towards the unburned gas, in fact, will spread out. But the portion which is concave towards the unburned gas eventually will create a cusp. Okay, and so the creation of cusp is one of the result or the consequences of the instability. And you can see this flame is a V flame. Remember, I spoke about a V flame, which is like a Bunsen flame, but stabilized at the burner by some rod, let's say at the center here. So this is a V flame, which is in a weakly turbulent stream. So the turbulence is like, it's like a disturbance here, a forced disturbance on the flame. And as a result, you see the region that separates the unburned from the burned gas, it's quite sharp, and you see the creation of those cusps, and that's the signature of the Dario-Landau instability. Another example is this turbulent flame here, which you also see these ridges being three-dimensional. Cusps are equivalent to ridges, so you see those ridges and cusps. And this is another example taken from a paper in the 50s by Uberoy. Actually, it's a nice example, which in a way we discussed before in this week. So we have seen that when the incoming velocity of the gas on a, say, coming out of a Bunsen burner is sufficiently high, then the flame is conical, and the angle depends on how fast this velocity is. In fact, the angle depends on the ratio of U, the velocity divided by the laminar flame speed. And so when you lower the velocity U, the flame becomes less and less pointed towards the burned gas, right? And eventually when capital U approach SL, in principle it's supposed to be flat. However, in reality, it doesn't flatten out. As you see in those examples, it keep on having these cusps which are at the two ends. And again, that's a consequence of the fact that too flat of a flame is not possible because of the instability, and therefore it creates this cusp-like behavior. Another example is the fact that in tubes, flames are typically curved. And they are curved like it's shown here. They are convex towards the unburned gas, and that's another consequence of the hydrodynamic instability. Okay. The next thing I want to add to the discussion is the inclusion of gravity. Now, suppose that now we examine the problem. Again, you have this perturbed flame in the presence of gravity. And if gravity is pointing downward, I call it minus G because I included in the equation a minus for the equation that I did not write down. No, actually I did. I wrote down the solution. So you see here you have the pressure, which has this additional hydrostatic pressure, right, which is with the density rho U for the unburned gas and rho B for the burned gas. Now, so if G is positive, right, because minus G is the gravity in the downward direction. So if G is positive in this description, we are talking of a flame propagating downwards against gravity. But this same description is good if you just put the unburned gas here and the burned gas here, and then G will be simply negative. The reason I mention that is because then I can do the analysis once and I don't have to do it twice for upward and downward. All I have to do is just change the sign of G and get the answer for both cases. So the question is, what happened to the stability question or to this planar flame if you account for gravity? Well, the only place where gravity enters the problem is through the jump relation of the pressure, because the pressure have this hydrostatic effect, and so eventually the pressure across the flame does have a contribution that comes from gravity. Okay, the mathematical detail, you can verify them later if you're interested. If you now go back and reanalyze the problem, the dispersion relation that you obtain is this, and easily check with G equal to 0, you obtain exactly the previous relation. But now it's interesting to examine, of course one can examine this full expression and ask when is omega positive or negative. It turned out that it's still always positive, but in other words, the flame is still always unstable. There are always disturbances that will grow. However, what we may want to understand is there a difference between the long wave and the short waves. And so the first thing we examine is K large. K large means short waves, right? The wavelength is the reciprocal of the wave number. So short waves. If K is large, then inside the square root, the term with K is small compared to the term with K squared. So this is negligible. And so the result is exactly what you had before. So gravity does not have an effect on the small waves, on the waves which are of small magnitude or small wavelength. However, the long waves, where k is small, when k is small, it's a k squared that is small, and so the answer is going to be the square root of this negative number minus s sigma lk. The negative of the square root of the negative number is imaginary. So omega is an imaginary quantity here, which is just this part with k squared, with k, but if you take it outside the square root, is the square root of k, and the second contribution will come from here. So the real part here is negative, which means that the very long waves are stabilized by gravity. So the long waves are stabilized by gravity, short waves are not affected by gravity. So since for full stability you need all waves to die out, then you still have the short waves that destabilize the system. However, just the consequence of this may be relevant for a later discussion. So that's the effect of gravity, and now the question is what happened. So far, I kept G positive. The question is what happened if G is negative. Well, if G is negative, nothing is affecting the short waves, but now the long wave that become real, right? Because it's also another negative G here, and so that become real, and so it's also unstable. So upward propagation are always unstable. Even the long waves become unstable. Downward propagation, the long waves are stabilized. And that's summarized here. In particular, you can see, for example, you can ask what is the wavelength lambda, which are stabilized by gravity, and you can determine from the previous relation that those are all the waves lambda that are bigger than that number, which is proportional to SL squared divided by G, which means that a slowly propagating flame would have a wider range of stability, okay? For upward propagation, gravity acts to always destabilize, so that doesn't help. Gravity does not help. Okay, so then the question is now, what are the consequences of the Dario-Landau instability? In other words, once the flame is unstable, to what form does it develop? And the second question is, what about the influence of diffusion? Because we have seen that the short wave, according to the Dario-Landau instability, become even more unstable. But we know that once the disturbances of the side of the flame thickness, this description is not valid. And so we have to improve that. And so these are the first few questions that we want to discuss. So the first one, the first one that I want to discuss is what is it's number 2, what is the influence of diffusion? And now to analyze the full system with diffusion and with thermal expansion is a very complicated mathematical problem. And so in the literature, the idea was the following: since the hydrodynamic instability keep on increasing with sigma, if sigma was 1, which means if I ignore the density variation across the flame, then this relation will give me that the flame is neutrally stable. It's neither stable nor unstable. In other words, I can filter out the hydrodynamic instability or the hydrodynamic disturbances by assuming that the density is constant across the flame, and then examine those other effects, okay, which are the effects of diffusion. So this is the first step we're going to take, and then the next step we're going to say, okay, what if we need to combine them both, okay, both effects. So now we, and remember that this is in principle, those are effects that are superimposed, because after all we are looking at linear stability, and in linear problem you can superimpose solutions. So it's not too bad to follow this, this trend, although it's not precise. So in the absence of density variation, the problem that we are facing is the equation for the temperature and the mass of the reactant, Y. It's interesting to see that the system of equations that include momentum, mass conservation, momentum conservation, energy, and species seem to decouple. Two of them give us a certain effect on the flame, and two others give us a different effect on the flame. So now we are focusing on this reactive diffusive system as if the flow is known, okay? And the flow is a simple planar, a planar flame, so the flow is simply uniform. Since it's not affected by density doesn't change, then it's a constant throughout. Okay, so we now analyze this structure. In other words, this is the basic structure, and now we ask what if the flame, which is located here where the reaction sheet is slightly perturbed. And well, the analysis is it's quite involved, and I'm not going to show you or discuss the detail, but I just want to focus on this little L here. In the description, to make it systematically or mathematically correct, one have to assume that the Lewis number is not too large. In fact, it's assumed to be close to 1 by a measure of 1 over beta. And so the little l is a measure of the deviation from 1. So little l is the positive when Lewis number is bigger than 1, negative when Lewis number is less than 1. Okay, so when we go through including perturbation, again, normal mode, we assume normal mode, the perturbation of the flame front or the reaction sheet of this foam, like before, where k is the wave number, omega is the growth rate. Again, you end up with a dispersion relation. Now, the dispersion relation is omega, which is the growth rate, as a function of the wave number. And the only parameter in the problem, remember, is in this problem, the only parameter is the Lewis number, which is the rate. Well, there is also an activation energy, but the activation energy is considered very large because it's done within the context of a large activation energy asymptotic. And so the only real parameter is the Lewis number. And so the Lewis number, which is expressed here in terms of this little l. And the question, as before, is what is the magnitude of omega? Stability is assured when omega real is negative for all k. Otherwise, the solution is unstable. Well, unfortunately, here we cannot deduce anything from dimensional analysis, so we still have to do the whole, we just have to discover it by constructing the full solution. So here is the dispersion relation that we obtain. It's a complicated cubic relation where these coefficients B0, B1, B2, B3 are all functions of the Lewis number and the wave number k. And the discussion of this cubic lead to some results. In particular, you see what you ask is, we know that what distinguishes between stable and unstable, it's when the growth rate or the real part of the growth rate is equal to 0. So if you set equal to 0, you obtain the curve that separates stable from unstable region. However, since omega is complex, then the imaginary part of omega enter in this discussion because this equation is a complex equation. So in fact, it's equivalent to two equations. One, when you decompose it into real and imaginary part. So there is a bit more to it than just setting equal to 0. You know, you have to set the real part and analyze the equation as they are. The result is described here. There are two neutrally stable curves. In other words, there are three regions. The region of stability, where the real part of omega is always negative, is between two values of the Lewis number which are around 1. In other words, 1 is less than 1. This critical value is slightly less than 1. This critical value is slightly above 1. So the flames are, as a result of diffusion thermal effect, right? Thermodiffusive effect, however you call them, the order doesn't matter, are stable in the vicinity of Lewis number equal to 1. When the Lewis number is much less than 1 or much bigger than 1, then you have an instability. And as we will discuss next, in this region you have cellular flames, and this region either pulsating or traveling waves along the flame front. Now the discussion is here. You see here is the perturbation of the flame, and it's the amplitude multiplied by e to the iky plus omega it. In other words, this is the imaginary part. It's multiplied by I. And then it's multiplied also by the real part. Now, when the flame is neutrally stable, namely not stable, not unstable, just on the verge of becoming unstable, then the real part is 0. So I set that equal to 0, so e to the 0 is 1, and that's what you get. Now, if omega I is 0, in other words, if there is no imaginary part, then the solution is simply a sinusoidal sine-cosine form of this type, and that is what the transition from the stable to the unstable region gives you. So it gives you, in that case, a flame that has this shape, e to the iky. So it's like a sinusoidal flame, a corrugated flame. That's exactly the cellular flame that is described here, because at the transition we found that the imaginary part is exactly equal to 0. If the imaginary part is not 0, then let's first suppose that k is 0. So if k is 0, then this expression just reduced to a, an amplitude e to the I omega t, which is a flat surface that oscillates in time, right? E to the I omega t, it's like a sine t, sine omega t. So just oscillate. So it's a pulsating flame. And if k is not equal to 0, then in addition to this pulsation, in fact, the shape is not flat, but it's rather corrugated. And so the time dependence is just a wave propagating along the surface at a speed which is c defined by omega I over k. So you can describe all the possibilities, and what we see is that the omega I is not 0 in this range of the parameter. So when the k equal to 0, which is on this line, you will get pulsating flame. So as you transition, as you change your mixture by changing the Lewis number from the left of this curve to the right of this curve, the flame is first stable and planar, and then as you cross that value just by changing the, say, the composition in order to make the Lewis number larger, then it will start oscillating spontaneously, okay? The same thing if you move in this direction. The flame is planar and stable, and if you change the composition such that to reduce the Lewis number, it will suddenly take this steady shape. Of course, there is a slight transition from flat to this steady cellular flame, but eventually it will take that shape, and that's the new shape that you would observe. Now, let's focus on cellular flames. Remember that the Lewis number is the ratio of the thermal diffusivity of the mixture divided by the binary mass diffusivity. This is thermal diffusivity. Binary mass diffusivity D of the deficient reactant, the binary diffusivity reactant inert, right? Okay, so by changing, in fact, the inert, you can change the Lewis number. And when I said before, if you change the Lewis number slightly, the flame will transition, say, from a planar to a pulsating or from a planar to cellular. All you have to do is change the dilution. And that's basically what people have done to observe this instability in the lab. Okay, so, but before this, I want to see in what range of Lewis number we expect to see what and what has been observed. So if you take hydrocarbon air flame, for example, thermal diffusivity is based on air, and it's approximately 0.19 centimeters squared per second. For propane nitrogen, the mass diffusivity, or the diffusivity of propane nitrogen, this binary diffusivity, is approximately 0.11, and oxygen nitrogen is approximately 0.22, okay? Now, for lean mixture, then D of the propane has to be considered, and so it's this ratio, 0.19 divided by 11 that gives you the appropriate Lewis number, and that's approximately 1.73. For rich mixture, rich hydrocarbon, propane as an example, then the ratio is 0.19 divided by 0.22 because the deficient component in a rich mixture is oxygen, okay? And so that ratio gives you 0.86. And so the little l, if you take the scale with beta and so on, is in the range between -3 and 11, okay? -3 for the rich, 11 for the lean. And indeed, it falls within that number that we have obtained in the theory. So for hydrocarbon, for example, you're going to obtain values in this range, and so you can indeed observe cellular flame, and they have been observed on the rich side of stoichiometry, okay, as expected from this description, right? The rich side gives you this end here. Except for methane, because methane has a Lewis number which is really not too far from 1, and so the variation are not significant, so methane fall in the range of more stable flame. But not quite, because, you know, there may be other things that could cause that it change a little bit, so sometimes some of the instability has been observed. So methane is not a very good example of the extreme, basically. But hydrogen air behave differently, and so instability will be observed in the lean side, because you see for hydrogen air, the ratio of thermal to mass diffusivity when it's a lean system, it's going to be 0.19 divided by 0.61, which is approximately this number for lean mixture, and so it's way in the unstable regime, right? It's -10, it's much more, it's in the left of -2. Okay, so in other words, the theory give a proper range of Lewis number, at least the correct trend as observation show. Now here is an explanation, if you like, of the cause or the reason for the instability. Remember, the instability is due to Lewis number effect or thermodiffusive effect. And remember that the Lewis number is the thermal diffusivity divided by the mass diffusivity. Okay, so if you look at a planar flame, then all the isotherms are parallel to each other, okay? And what you have is heat conducted away from the flame and fuel diffusing towards the flame to support the flame, okay? And so they are in balance and the flame is stable. But the Lewis number is essentially close to 1 here because the two arrows are approximately the same, namely the diffusivity of mass towards the flame and heat conduction away from the flame are more or less in balance when Lewis number is 1. Now, if you have a corrugated flame, then the isotherms will first of all follow this corrugation, but eventually far away they will flatten out because far away the mixture is homogeneous, and so they will again become parallel lines, okay? So what you see is that you have very sharp gradient in intrusion towards the unburned gas and a much weaker gradient in the region which is intruding towards the burned gas. Now, because when the Lewis number is less than 1, which means that mass diffusion is much stronger or much more effective than heat conducted away, then there will be much more, you see, before I get there, the sharp gradient or the weak gradient in these two regions that I have emphasized, it's also equivalent to the fact that you have, because the flame is corrugated, you have also transverse diffusion. So heat and mass is also, heat is conducted also on the side, whereas mass is focusing in. Whereas in this region, it's more focusing out because it's normally towards the normal, right? So that's equivalent to that statement that I said. But anyway, if the Lewis number is less than 1, which means that heat conduction is weaker than mass diffusion, right? Thermal diffusivity is less than mass diffusivity. Then you see the arrow here is smaller than this one. So this segment of the flame is replenished with reactant at a faster rate than it loses heat. And as a consequence, it will propagate faster. And it propagates faster than a segment here where it is still larger than the heat conducted away, but because of the spreading of the smaller gradient, it will be propagating faster than a planar flame, but much less than in this region. So overall, you're going to get this region propagating faster out than those, and it will maintain or sustain the instability. Okay? Here is a cellular flame taken in the lab of Quinar in 1990. You see how this is a three-dimensional cellular flame, but if you take any cut like this, it's essentially this steady sinusoidal shape that you have seen. What you see in this photograph is that the cell size are, on the average, they have the same size, or on the average there is a representative cell size. Unfortunately, the theory is not complete here. Well, in some sense it may be, but if we focus, for example, on this region to study the cellular instability, what we see is that if you are on the left, on the right of -2, in other words, if the Lewis number is bigger than -2, then the flame must be stable, and here unstable. And indeed, the growth rate show, right, that when L is bigger than -2, the growth rate immediately decreases as a function of K, so it's always negative and the flame is stable, whereas for stable flame you have a range of wave number and therefore of wavelength that the disturbance grow. Omega is positive. And so in a way, perhaps a measure of the cell is either this K star or the K that represent the dimension of your burner, okay? The dimension of the burner, let's say L, must be, you cannot have waves which are larger than this dimension because they're not going to affect the flame. They are bigger than the size of the flame. And so if this is a resolution that explains the same size, the cell size, it's not a sufficient one, it's not a good one, because then it will depend on the size of the burner, which is really not what we have seen in the experiment. Well, when we come to the combined effect in a little while, we will see how this may be improved, or maybe we can explain that cell size independent of this argument. Okay, so the next one that I'm focusing on here, it's the traveling waves, so the pulsating flames, and I'm going to go through that quickly. If you focus on the planar pulsating flame, then the critical Lewis number, which correspond to this value of 4 times 1 plus square root of 3, turn out to be a Lewis number which is, well, this quantity turned out to be very large, which implied that the Lewis number have to be extremely large, and that's usually not, there are no common combustible mixture that have such a large Lewis number. However, that critical value, namely this one here, can be brought down closer to Lewis number 1, in other words, making more common combustible mixture possible to exhibit this instability if you add heat losses. Heat losses diminish this range of stability. Heat losses promote the instability and cause this range to be narrower or smaller, this range of stability. And so, for example, people have observed pulsating flame on top of burners, because at the near burners, the flat flame is subject to heat loss, and if the Lewis number is sufficiently large, then the flame is seen to pulsate. Okay, so this is that. and the combined effect. Let's take a break and then we come back to it.